So in chemistry, when we want to measure the energy changes associated with reactions, we call them enthalpy changes. And the symbol associated with enthalpy change is delta H, where the delta symbol means a change and H means enthalpy. Okay, when chemical reactions occur, there are generally two kinds of energy changes that happen. Sometimes the change is endothermic and sometimes the change is exothermic. Endothermic can be broken down into, well, the word into, and thermic meaning heat. And therefore, endothermic changes involve heat going into the reaction, going into the system. Exothermic can be broken down as exits and thermic meaning heat. So in exothermic changes, we have heat exiting the reaction. If we look down below at these diagrams, in one of them, we see that the system, or the change process that is occurring, and we can see that these arrows that represent heat, the arrows are exiting the system and going to the surroundings. Therefore, this diagram represents an exothermic process. The exothermic process is releasing heat to the surroundings. If we look at the one on the right, we see that the heat energy is being shown going into the system. And therefore, since heat is going into the system, heat is being absorbed, and we say this is an endothermic process. If we think about what would happen to the temperature of the surroundings in each of these, well, if heat is going into the surroundings, that would be in the exothermic system over here. The heat is exiting our reaction, our system, and it's going into the surroundings. So for our surroundings, the surroundings are gaining energy, and therefore we'll end up with a positive change in temperature, or a temperature increase. In an exothermic process, the surroundings gain energy. If we flip that for an endothermic process, I answered this only for an exothermic process. So my answer for endothermic, I'll put up here. In an endothermic process, we're looking over here at the one on the right. For an endothermic process, energy is going into the reaction or into the chemicals, and that energy has to come from somewhere. That energy is coming from the surroundings. So the surroundings are losing energy and that means that there's going to be a negative temperature change, or the temperature is going to decrease in an endothermic process. So remember, you and I are part of the surroundings. We are not part of the reaction that's taking place. So we are outside of that reaction. So if that reaction releases heat to us, then we're going to feel warm and our temperature will go up. We gain energy when the system loses energy. And then vice versa, if we are looking at a chemical reaction or feeling a chemical reaction that's taking place and there's heat going into it, then that energy is going to come from us. And therefore, we will lose energy and our temperature will go down. So notice that the energy changes are always opposite for the system and for the surroundings. So when something is exothermic, the surroundings have a positive temperature change, but the system itself actually loses energy. And using the delta H symbol, we would say that the system is negative delta H. So the system has a negative energy change, and the surroundings have a positive energy change. Energy is always conserved, so if it goes up in one place, it must come down in another place. If we do the same thing for endothermic, in endothermic reactions, we feel cold because and our temperature will go down if we are part of the surroundings, because the energy is going into the system. So endo means into. Where does it go? It goes into the chemicals, into the system. So the chemicals and the system gain potential energy, and that has to come from somewhere. So that comes from the surroundings. So the signs will always be opposite for the system and the surroundings. Based on what we know about combustion reactions, well, combustion reactions feel really warm. Combustion reactions involve burning things, involve fire, and therefore combustion reactions make the temperature of the surroundings go up. So that matches an exothermic reaction. The reason why combustion reactions are so useful is because they release a lot of energy. Okay, so in summary, exothermic changes have negative delta H values. They release energy, and that makes the temperature of the surroundings go up. On the other side, endothermic changes have a positive enthalpy change. They absorb energy, and that means that the temperature around an endothermic process will have a negative temperature change or get colder. Okay, how does this connect to the covalent bonding that we have been talking about? So we should know that chemical bonds are actually attractions. So two atoms are held together. And we should also know, if we think about what a chemical reaction is, a chemical reaction is the rearrangement of atoms. So we don't actually change the atoms themselves, but we change how they are bonded. And so in a chemical reaction, you have to first break chemical bonds for the reactants, and then you put the atoms back together to form products, and therefore you're forming new bonds in the products. Anytime that we break a chemical bond, that will take energy because, like I said before, a chemical bond is an attraction. Think of it like two magnets being stuck together, north and south poles, because they are attracted magnetically. It would take energy to pull those magnets apart. So it's always, well, I'll pause because the question is at the end of the page. Then if we flip that, when atoms come together and they form bonds, that will always release energy. So if we think about a chemical reaction, it involves basically two phases. Energy has to be put in to break bonds, and that leads to separated atoms, which has been illustrated here. And then when those separated atoms come back together and they form new bonds to make products, then we're going to have energy released or energy out. A more specific example shows methane reacting with oxygen to form carbon dioxide and water. These are the reactants, these are the separated atoms, and these are the products. So which process is endothermic and which process is exothermic? Well, if breaking bonds involves energy in, then that is endothermic for bonds breaking. And which is exothermic? Bond forming is exothermic because it involves an energy release. So if we showed this on a diagram, we start with reactants. The first thing we have to do is break bonds, and breaking bonds is going to take energy. So that's energy uphill. We have to put in energy, so we'd say positive delta H, to break the bonds apart. At that point, we will have separated atoms. And then when separated atoms come back together and form new bonds, that will involve an energy release. And we'll end up with our products. And so on this part, we're showing bonds forming. So no matter what the reaction, it's always going to take energy, or you'll have to put energy in to break bonds, and then you'll get energy back out when new bonds form. This is summarized here. And now you're being shown some synthesis questions. Okay, if we look at the two diagrams, which diagram is exothermic and which one is endothermic? Well, if I look at the diagram on the left, I can see that there's a certain amount of energy that I have to put in for breaking bonds, and then there's a bunch of energy that I get out when the bonds form. And I can see that the energy out is more than the energy in. That tells me this is going to be exothermic. I know that exothermic reactions release energy. And just how much energy is the difference between where I start and where I end. And so right here it says delta H is less than 0. So that means we have a negative delta H value, which we should associate with exothermic reactions. A negative delta H will lead to a positive delta T for the surroundings because there's energy released. I could use the other arguments to talk about why this is endothermic. I can see that there's more energy put in, so there's a bigger positive uphill that I'm going to get back out when the new bonds form, and therefore overall it's an energy uphill change. And so this is positive delta H, so energy has to be net put in to make this reaction happen. And then we could label any arrows uphill as bonds breaking, and any downhill arrows as bonds forming. Now the other thing in this diagram that you could label, we'll use a different color, this part of the hill is called the activation energy. And in this one, the activation energy is this entire thing. And activation energy is the minimum energy required to get a reaction to successfully occur. So unless the reactants have enough energy, they won't start reacting. And that's why even though things like methane and other fuels are really good at burning and combusting once they get going, they still require a spark or an initial flame to actually get them reacting in the first place. And that connects with that activation energy concept. So usually there's some minimum energy requirement for reactants to begin reacting. Once a combustion reaction starts, the reaction is releasing enough energy that it can keep itself going. But at first you need to often add that energy somehow. If we look at the ones above, is there more energy needed to break bonds in the reactants or released from forming new bonds in an exothermic reaction? Well, in an exothermic reaction, if I look at the diagram on the left, I can see that the energy out is greater than the energy in. The energy out is from the formation of bonds, and the energy in is from the breaking of bonds. Therefore, there's more energy with the formation than there is with the breaking. The formed bonds are in the products, and the broken bonds were in the reactants. So if I put all that together, I can tell that the reactant bonds, these ones over here must have been weaker because they don't add up to as much energy as the bonds in the products, which must be stronger. So in exothermic reactions, overall, the total strength of the product bonds is greater than the strength of the bonds in the reactants. Okay, looking at these symbols, we should be able to tell if they're exo or endothermic. If I see negative enthalpy changes, I know those are exothermic. And if I see a positive enthalpy change, I know that's endothermic. I also know that the change on the delta H is always opposite to the change of temperature of the surroundings. They always have opposite energy changes, so opposite symbols. So if it's exo and I have a negative delta H, I'm going to have a positive delta T. So the first and the last one here, A and C, are exothermic reactions, and they would result in temperature increases in the surroundings, whereas the middle one, which is endothermic, would have a decrease in the temperature of the surroundings. And then the final question, generally speaking, more stable substances have lower potential energy. Use diagram A and B on the previous page to answer the following questions. So lower potential energy, if we look at these diagrams, in the exothermic one, the products end up lower in terms of their potential energy or their overall enthalpy. Whereas in an endothermic reaction, this is y-axis is potential energy. The reactants start lower and the products end up higher because I've put energy in. So come back to the questions. Is there more energy stored in the reactants or the products in diagram A? There's more energy in the reactants. And that's if we look again at that diagram, the reactants are up here and the products are down lower because there's been a net energy release. So in an exothermic reaction, the reactants have more energy, and I can see that they have a higher potential energy on that diagram. So what's more stable? Well, up here it says more stable substances have lower potential energy. So the products have lower potential energy and therefore they are more stable. So like in a combustion reaction, we start off with a hydrocarbon and oxygen, and we end up with carbon dioxide and water. And that means that carbon dioxide and water are more stable than the hydrocarbon and the oxygen that we began with. Then if you look at diagram B, we can flip everything. In an endothermic reaction, we're actually creating products that have more energy. And are the reactants or products more stable? In an endothermic reaction, the reactants are more stable. So these ones are about endothermic, whereas parts A and B, this was about exothermic.